Hello student, welcome to my channel Learn Physics. Today I will be discussing a one-shot video of surface tension. My discussions are first of all surface tension, surface energy, relation between surface tension and surface energy, expression for work done, axis pressure, angle of contact, nature of meniscus of liquid surface, capillarity, and different types of numerical of all topics. This video will be extremely helpful to build up your concept as well as revision of the chapter. For revision of whole chapters, I uploaded a playlist of one-shot video of 10 chapters of class 11. So this one-shot video will also be extremely helpful for your concept building measure as well as final revision for class 11, neet, main and advanced. Okay? Please like, share, comment on this, and to learn physics easily and quickly, subscribe my channel. Okay, now let's start. We know all liquid possess special property, a tendency to minimize its surface area. This property of tendency to minimize the surface area of liquid is called surface tension. Now, from our practical experience, we know that small water droplet and small amount of mercury takes the shape of a sphere. In absence of external forces, all liquid takes the shape of a sphere. Now, for a given volume, the surface area of a sphere is minimum. So all liquid has a natural tendency to take the shape of a sphere. Now if a clean needle is placed on a water, the needle floats and the water under the needle slightly depressed. We often observe that the spider and mosquito walks on water, and water surface below the legs of spider or mosquito slightly depressed. So from our above experience, we know that the free surface of liquid behaves like a stretched rubber membrane. So these are the property of surface tension. Now definition of surface tension. If an imaginary line is drawn on the surface of liquid, then a force normal to the line drawn and tangent to the liquid surface acts. This force per unit length on either side of the line drawn is called surface tension. Therefore, surface tension S equals to tangential force divided by length of line of contact. Okay? Now, tangential force F, length of line of contact L. So, look at this. Tangential force, this is the S into L. Okay, this is the force of surface tension. Okay, understood? Now what is the unit? Look at this, the unit of surface tension Newton per meter, and dimension, look at this, its dimension is MLT minus 2 by L, that is, this is the MT minus 2. Okay, understood? A numerical of force of surface tension. Look at this, A rectangular glass slab measures 0.1 meter, 0.01 meter and 0.002 meter is immersed half in water, keeping length and height horizontal. As given, we have to calculate the force of surface tension. Look at this. This is the glass slab. Look at this. This is the length, this is the height, and this is the breadth. Look at this. Here, length and height horizontal. So look at this. This is the length and this is the height. So these are horizontal. Now what is the length of line of contact? Look at this. This is the length of line of contact. This is the length of line of contact. This is the length of line of contact, and this is the length of line of contact. Okay. So total length of line of contact 2 into length plus 2 into height. Okay. Understood? So total length of line of contact equal to 2 into length. This is the length, so this is the 0.1 plus this is the height, so this is the 0.002. Okay, so look at this. This is the 2 into 0.102, so this equal to 0.204 meter. Okay, now we have to calculate the force of surface tension. Look at this. The force of surface tension F equals to surface tension into total length of line of contact. Now look at this, the 0.072 into length of line of contact, this is the 0.204, this is the Newton. Okay, understood? So look at this, this is the 7.2 into 0.204 into 10 to the power minus 2 Newton. Okay, this is the 1.44 into 10 to the power minus 2 Newton is the force due to surface tension. Okay, understood? Next, now surface energy. The free surface of liquid behaves as a stretched membrane. Therefore, work is done to increase its area. This work is stored as a potential energy in the surface. This potential energy per unit increase of surface area is called surface energy. Suppose delta W be the work done to increase the surface area delta A, then surface energy E is equal to delta W by delta A. What is its unit? Look at this, work done by area, so its unit is joule per meter square. What is dimension? Look at this, its dimension is here ml square t minus 2 and area is the L square. Therefore, its dimension is mt minus 2, just as the dimension of surface tension. Okay, now its CGS unit. Its CGS unit is arc divided by centimeter square. Now we have to establish the relation between joule per meter square and arc per centimeter square. Now look at this, 1 arc per centimeter square, this equal to, this is the 10 to the power minus 7 joule, and 1 centimeter square means 10 to the power minus 4 meter square. So this is the 10 to the power minus 4 meter square. So this is the 10 to the power minus 3 joule per meter square. Okay, now the surface energy of water is 72 arc per centimeter square. Now what is its value in SI system? If arc per centimeter square is converted into joule per meter square, so we have to multiply it by 10 to the power minus 3. So look at this, this is the 72 into 10 to the power minus 3 joule per meter square. So this is the 0.072 joule per meter square. Okay, understood? Now we have to establish the relation between surface energy and surface tension. Okay, look at this. This is a rectangular frame and a light rod AB on this rectangular frame. Now this space is filled with the soft film. So this light rod is attracted inwardly. Now to keep it balanced, the outward force should be force is equal to surface tension and length of line of contact. Look at this. Here length of line of contact in outward direction is L and inner direction is L. So this is the 2L. Now amount of work done to displace AB by the distance delta x, this equals to delta W is force into delta x. So look at this. This force is equal to 2SL into delta x. Now what will be the increase of surface area? Look at this. The increase of surface area is L into delta x and inner side is also L into delta x. So increase of surface area delta A is equal to 2 into L into delta x. Now what is the surface energy? Surface energy is work done per unit increase of surface area. So this is the delta W by delta A. So look at this. This is the 2SL delta x divided by 2L delta x. So look at this. This. So this is the S. Therefore surface energy and surface tension are same. Okay. Now some important relations about surface tension. Okay. Now amount of work done to form a bubble of radius r. Look at this. We know work done delta W is equal to surface energy E into delta A. Now we know surface energy is equal to surface tension, so S into delta A. Now what is the delta A of this bubble? Look at this. The delta A of this bubble is, this is the 4 pi r square. Therefore amount of work done to form a bubble of radius smaller is 4 pi r square into S. In case of soft bubble, this work done is equal to 4 pi r square into 2S because soft bubble has two surfaces, inner surface and outer surface. Okay, understood? Now amount of work done to increase its radius from small r to capital R. Okay, look at this. This is the capital R. Now its initial surface area is 4 pi r square. The final surface area delta A dash, this is the 4 pi capital R square. So increase of surface area this minus this. Okay, understood? Therefore work done to increase its radius from smaller to capital R, this is the S into 4 pi into this area minus this area. So this is the r square minus small r square. In case of soap bubble, S is replaced by 2S because soap bubble has two surface area. Okay, understood? Now next. Now a numerical. Find amount of work done to form a soap bubble of radius 5 cm. The surface tension of soap water solution is 70 dyne per centimeter. Now look at this. A soap bubble has two surfaces, inner surface and outer surface. So work done delta W, this is the 4 pi small r square into 2S. Okay. Now this is the 8 into pi into r square into S. Look at this. This is the 8 pi. R is equal to 5 centimeter. So look at this. This is the 5 square and S is equal to, this is the 70. So look at this. 5 square into 8, so this is the 200 pi into 70. This is the arc, therefore this is the 14000 pi arc is the amount of work done to form a soft bubble of radius 5 centimeter. Okay, next, now a numerical. The radius of a soft bubble increases from 1 centimeter to 3 centimeter. We have to calculate the work done for this purpose. The surface tension of soft solution is equal to 26 dyne per centimeter. Okay, now look at this, the work done delta W, this is the, it has two surface area, so this is the 2s into increment of surface area. What is the increment of surface area? Look at this, this is the 4 pi into capital R square minus small r square. Look at this, here small r given, capital R given, and surface tension S is also given. So look at this, this is the 8 pi, S is the 26, and this is the 3 square into 1 square. So look at this, this is the 8 pi into 26, and this is the 9 minus 1. So look at this, this is the 64 pi into 26, this is the arc, this is the 1664 pi arc is the amount of work done. Okay, understood? Next, look at this. Now look at this, a bubble of radius capital R. Look at this, this is a bubble of radius capital R. Okay, splits into n number identical bubble, each of radius smaller. Look at this, this is the n number of identical bubble, each of radius smaller. Okay, now we have to calculate work done for this purpose. Now we know work done is equal to delta W is the S into increment of surface area. Okay, now look at this, when a bubble of radius R splits into n number of identical bubbles, the volume of n number identical bubble is equal to volume of this. Now what is the volume of this? Look at this, volume of this bubble is 4/3 pi capital R cube. Now volume of n number identical bubble, each of radius R, this equal to n into 4/3 pi into R cube. Okay, no problem. Look at this, this and this cancel out. Therefore capital R cube is n into small r cube. Therefore capital R is the n to the power 1/3 smaller. Okay, understood? Now we have to calculate the increment of surface area. Now increment of surface area delta A is equal to n into surface area of smaller bubbles. So look at this, n into 4 pi r square minus surface area of this big bubble. So this is the 4 pi capital R square. Now small r can be replaced from this equation. So look at this, this is the n into 4 pi, this is the capital R by n to the power 1/3. Look at this, small r equals to r divided by n to the power 1/3. So this is the square minus 4 pi r square. Okay, now look at this, here n to the power 1/3 square, so n to the power 2/3. So here n by n to the power 2/3 into 4 pi r square minus 4 pi r square. Okay, now look at this, from this equation you can write 4 pi r square. Look at this, n by n to the power 2/3, that is n to the power 1/3. Look at this, this is the n to the power 1/3 minus 1. Okay, so look at this, the work done delta W, look at this, this is the S into delta A. So work done is the 4 pi r square into S into n to the power 1/3 minus 1. Okay, understood? Next, look at this, if n number smaller bubbles, each of radius smaller, coalesce to form a large bubble of radius capital R, then surface area decreases. therefore energy released. The amount of energy released is same as this. So amount of energy released in the reverse process, this is the 4 pi r square into s into n to the power 1/3 minus 1. Okay, now I will be solving two numericals. Now look at this, and water bubble of radius 1 millimeter splits into 10 to the power 6 number of identical smaller bubble. What will be the work done for this purpose? Now work done for this purpose, this is the delta W, so this is the 4 pi capital R square into S, here n to the power 1/3 minus 1. Look at this, here delta W equal to, this is the 4 pi, now 1 millimeter should be converted into centimeter. So look at this, this is the 1/10 whole square, and S is equal to 72 dyne per centimeter. So look at this, this is the 72, and look at this, this is the 10 to the power 6 to the power 1/3 minus 1. Okay, now look at this, this is the 4 pi into 72 into 10 to the power minus 2. Look at this, this is the 100 minus 1. So look at this, this is the 99. So look at this, this is the 396 pi into 72 into 10 to the power minus 2 arg is the amount of work done. Now look at this, so this becomes 3.96 pi into 72 arg. Okay, now look at this, this becomes, now look at this, this becomes almost 288 pi arg is the amount of work done. Okay, understood? Now thousands number of bubble, each of radius 0.01 centimeter, coalesce to form a large bubble of radius capital R. Now we have to calculate the decrease of surface energy or energy released. So look at this, when smaller bubble forms a larger bubble of radius capital R, the R capital R becomes n to the power 1/3 smaller. Now n means this is the 1000 to the power 1/3, and this is the 0.01 centimeter. Now look at this, this is the 10. So this is the 10 into 0.01 centimeter. So look at this, this is the 0.1 centimeter. Okay, understood? Now increment, now work done. Now energy released or decrease of energy. Now energy release or decrease of energy. Look at this, this is the 4 pi capital R square into S, this is the n to the power 1/3 minus 1. Look at this, n to the power 1/3 means 10. So here 4 pi R is the 0.1 whole square, S is the 72, and this is the 10 minus 1. Okay, understood? Now look at this, this is the 9 into 4. So this is the 36 pi into 10 to the power minus 2 into 72. Okay, this equal to almost 26 pi arg is the energy released or a decrease of surface energy. Okay, now excess pressure of a bubble. Look at this, the pressure, look at this, this is a bubble of radius smaller. Its pressure inside greater than pressure outside. So difference of this pressure, that is P minus P naught, is called excess pressure. So excess pressure P minus P naught, this equal to, this is the 2S by R, where R is the radius of this bubble and where S is the surface tension of it. Okay. Now in case of soft bubble, has two surface. This is the inner surface and this is the outer surface. So in case of soft bubble, this is the P minus P naught. This is the small p axis pressure. This is the 2 into 2s by r. So this is the 4s by r. Okay, understood? Now, what is the total pressure inside the soft bubble? Look at this. The total pressure P equal to, this is the P naught plus 4s by r. Okay, in case of soft bubble. In case of other bubble, P equal to, this is the P naught plus 2s by r is the total pressure acting on it. Okay, if this bubble is formed at the depth h of liquid column. Okay, now look at this. This is the liquid column or depth h. So look at this. This is the radius r. So total pressure, look at this. This is the atmospheric pressure plus pressure of the liquid column plus excess pressure. So P equal to, this is the atmospheric pressure plus pressure of liquid column plus excess pressure, that is the small p. So this becomes P naught plus h rho g plus 2s by r. Okay, understood? Next, now radius of curvature of common surface. Now look at this. These two bubbles are in contact. We have to calculate the radius of curvature of this common surface. Radius of the smaller bubble smaller and radius of the bigger bubble is capital R. Now we have to calculate the radius of curvature of this surface. Suppose this is the R naught. Now look at this. The axis pressure in the smaller bubble side is greater than the axis pressure of bigger bubble side. So look at this, the net pressure. This becomes P1 minus P2. Because axis pressure small p is inversely proportional to R. Smaller the bubble, greater the pressure. That is why P1 greater than P2. Now the net pressure small p, this is the P1 minus P2. Look at this, the radius of curvature of the common surface is R naught. So look at this, this is the 2s by R naught equal to, this is the 2s by smaller, this is the 2s by capital R. Now look at this, from here 1 by R naught is equal to 1 by R minus 1 by capital R. Okay, understood? Next, now a numerical on axis pressure. Look at this, this is a mercury bubble. Now look at this, this is a mercury bubble of radius 2 mm. Surface tension of it is 0.464 Newton per meter. We have to calculate the axis pressure. Now look at this, the axis pressure P equal to, this is the 2s by R. Now S is the 0.464. So look at this, 2 into 0.464 and radius 2 mm, 2 into 10 to the power minus 3 meter. So look at this, 0.464 into 10 to the power minus 3 Pascal equal to, look at this, 464 Pascal is the axis pressure exerted by liquid surface in contact with air. Okay, understood? Now look at this, a numerical relating to axis pressure. Look at this, this is a mercury bubble of radius 4 mm. Now we have to calculate force on 1 mm square on its surface by the atmospheric pressure, by the total pressure and the axis pressure. That is the force F naught due to the atmospheric pressure, this is a pressure into area, and force by the mercury below it. So look at this, this force is the total pressure P plus small p into A, and finally force acting by the mercury surface in contact with air, that is this force is the F is equal to, this is the small p into A, that is this minus this. Okay, now look at this, the first of all force exerted due to atmospheric pressure, this is P naught into A. Now P naught is the 10 to the power 5 Newton per meter square, and this is the 1 millimeter square. Now if millimeter square is converted into meter square, this becomes 10 to the power minus 6 meter square. Okay, sorry, this is the meter square. Now this and this cancel out, so this is the 0.1 Newton is the force acting on 1 millimeter square area due to atmospheric pressure P naught. Okay, now the force exerted by the mercury F equals to, this is the P naught plus small p into A. Now so this equals to, this is the P naught into A plus small p into A. Look at this, P naught into A, this is the 0.1 Newton plus small p. Look at this, this is the 2s by R into A. Now this is the 0.1 Newton plus 2 into surface tension is the 0.465 divided by R, 4 into 10 to the power minus 3 into area, this is the 10 to the power minus 6. Okay, this is the unit is Newton. So this is the 0.1 Newton, and this is the, look at this, this is the 2 into 465 divided by 4 into 10 to the power minus 6 Newton. So look at this, this and this 2. So this is the 4 now. So look at this, this is the 0.1 Newton plus, look at this, this is the 2 into 10 to the power minus 6 Newton. So total force, this is the 0.1000232 Newton. Okay, and force exerted by the mercury surface in contact with air, so this is the this force. So finally small f is equal to, this is the small p into A, so this is the this, therefore 232 into 10 to the power minus 6 Newton is force exerted by the mercury surface in contact with air. Okay, now look at these two mercury drops of radius 3 mm and 4 mm coalesce to form a drop isothermally in free space. Find the radius of the bigger drop. Now radius of one drop is 3 mm and radius of other drop is 4 mm. So look at this, this is the R1 is equal to 3 mm and R2 is equal to 4 mm. Look at this, this is an isothermal process. So the product of pressure into volume is constant and it is in free space. So pressure of the bubble, look at this, pressure of this bubble is only excess pressure. Okay, this is the 4 mm, this is the 3 mm. Now pressure in it is the, look at this, 2s by 3. Now pressure in it P1, this is the pressure in it, this is the only excess pressure 2s by 4. Okay, now look at this, here P1 V1 plus P2 V2, this equal to P into V, where P1 is the excess pressure of first, V1 is volume of it, and P2 V2 is the pressure and volume of this, and PV is the pressure and volume of the bigger bubble. Okay, now look at this, this is the 2s by 3 into here 4/3 pi, this is the 3 cube. Now this is the 2s by 4, this is the 4/3 pi into 4 cube. Okay, and this is the 2s by r, and this is the 4/3 pi capital R cube. Okay, now look at this, 4/3 pi, 4/3 pi, 4/3 pi cancel out, 2s, 2s, 2s cancel out. So we get 3 cube by 3 plus 4 cube by 4 equal to r cube by r. So look at this, r square is equal to, this is the 3 square plus 4 square. So this is the 9 plus 16. So this is the 25. So this is the 5 square. So r is equal to 5. Therefore radius of the big bubble So radius of the bigger bubble is equal to 5 millimeter. Okay, understood? Next, if a tangent is drawn on the liquid surface from the point of contact from solid and liquid, then angle made by the tangent with the solid surface inside the liquid is called angle of contact. Now look at this. Here tangent drawn on the liquid surface from the point of contact between solid and liquid, then angle made by the tangent with the solid surface inside the liquid is called angle of contact. The liquid which does not weight solid, the angle of contact is obtuse. The liquid which weights solid, the angle of contact is acute. Okay, now we have to discuss the nature of liquid meniscus. Look at this. Suppose this is a solid surface. Suppose liquid meniscus like this. Okay, this is the liquid meniscus. Look at this. This is the point of contact between the liquid and solid. If a tangent is drawn on the liquid surface, then angle made by the tangent with the solid surface inside the liquid is called angle of contact. Now we have to discuss the nature of the meniscus of the free surface of liquid. Now look at this. We have to calculate the forces acting on the liquid molecules in contact with the solid. Look at this. Here forces acting is the adhesive force by the solid molecule. This is the Fa. Now the cohesive force acting by the neighboring liquid molecule is the Fc. And finally this is the weight of the liquid molecule. Okay, so forces acting on the liquid molecule in contact with the solid surface, this is the Fa, Fc and W. Now the resultant of three force determines the nature of the meniscus. Now what is the component of Fc along this direction? This is the Fc cos theta. Okay, now what is the component of this along this direction? Look at this. This is the Fc sin theta. Okay, if adhesive force Fa greater than Fc sin theta, then the meniscus is concave, just like water meniscus in narrow glass tube. Okay, if Fa is equal to Fc sin theta, then meniscus is plane. Okay, just like water in a narrow silver tube. Okay, if Fa less than Fc sin theta, the meniscus is convex, just like the mercury meniscus in narrow glass tube. Okay, now capillarity. The ascent and descent of liquid in a narrow capillary tube is called capillarity. Okay, the liquid which weighs solid, the liquid rises in the capillary tube. The liquid which does not weight solid, the liquid descends in the capillary tube. The height, ascent or descent of liquid column in a narrow capillary tube of radius r is given by H equal to 2s cos theta divided by r rho g, where s is the surface tension of the liquid, rho is the density of the liquid and g is the acceleration due to gravity. Okay, now the derivation of this formula is obtained from the concept of excess pressure. Now we know that the pressure in the convex side of a bubble is less than pressure on concave side. Now look at this. The pressure in the free surface is equal to P naught. Okay, so pressure just inside the free surface, this is the P naught minus 2s by radius of the meniscus. Okay, so look at this, the total pressure, look at this, the total pressure is equal to P naught minus 2s by r plus h rho g. This is equal to atmospheric pressure P naught. Now this and this cancel out. So look at this. This is the H rho G equal to 2S by R. Therefore H equal to 2S by R rho G. Now look at this. Capital R is the radius of the meniscus. Smaller is the, look at this, smaller is the radius of the capillary tube. If theta be the angle of contact, then the relation between capital R and smaller is equal to smaller by capital R. This equal to cos theta. And now capital R is replaced by, this is the smaller by cos theta. So look at this. This is the 2S divided by R by cos theta rho G. So this is the 2S cos theta divided by R rho G. Okay. Now Jurin's law. The height of liquid column in a narrow capillary tube is inversely proportional to radius of the capillary tube. That is H proportionate 1 by R. That is, smaller the radius, greater the height of the liquid column. Now if we draw a graph between H and R, the graph becomes rectangular hyperbola. Okay. Now some important questions on capillarity. If the height of the liquid column is insufficient length, that is the length of the capillary tube less than the height ascended by the liquid. Here radius of curvature, look at this, here radius of curvature in the free space increases in such a way that height of the liquid column is equal to length of the pipe. Look at this, here radius of curvature is small, here radius of curvature is more. Okay, understood? Now what happens if the experiment of capillarity is done in the gravity free space? In this case, look at this, G becomes 0. If G becomes 0, so H becomes infinity. Okay, in this case, the ascent of the liquid column is not infinity. The height of the liquid column is just the length of the capillary tube. If height of the liquid column, suppose 10 cm, length of the capillary tube is 20 cm. If it is kept in the gravity free space, then height of the liquid column is equal to length of the tube, that is 20 cm. Okay. Now what happens if the capillary tube inclined by an angle theta with the horizontal? In this case, the height of the liquid column in the capillary tube remains same. Look at this, here this is the height H, so height remains same. So length becomes, look at this, if this is theta, this is also theta. So length L becomes, look at this is the length L, this is the height H. So H by L, this is the sin theta. So L equal to H by sin theta. Therefore H cosec theta. So length of the liquid column in the capillary tube becomes H cosec theta. Okay, understood? Now some numericals. Now look at this, the radius of a capillary tube, this is the 0.2 mm. Surface tension of water is this equal to 0.075. Density 1000 kg per meter cube and G is 10 meter per second square. Now we have to calculate the height of water column in this capillary tube. Suppose this is the H. Now H is equal to 2S cos theta divided by R rho G. Now theta is taken as 0. So look at this, this is the 2, S is the 0.075, R is the 0.2 into 10 to the power minus 3 meter, rho, this is the 1000, okay, and G is the 10. Now look at this, this and this cancel out. Look at this, 10 into 0.2, so this is the 2, therefore this is the 0.075 meter is the height of liquid column. That is, this is the 7.5 centimeter is the height of water column in the capillary tube. Okay, understood? Many thanks for watching this video. This one shot video will be extremely helpful for class 11, NEET, main and advanced. Please like, share the video. To learn physics quickly and easily, subscribe my channel. Okay, thank you.